Okay. How are y'all doing? Good? Thumbs up? Alright. How we doing on proposals? Out there? Sort of? Yeah? Okay. Good. Yeah, nothing more to say. Just get them turned in. Shouldn't be too much of a burden, but you know, one thing that keeps coming up is people keep asking about. There are certain people who they haven't found another team member yet. Yeah, go ahead. Go ahead.
Okay.
Go ahead. Yeah.
We were wondering how exactly you want us to turn it in. It says just one person turn it in.
Yeah. So what happens on? Yeah, maybe I should explain this better. What happens on Canvas is that you can set up these kind of group.
Should we do it?
Yeah. So like when you submit this, you'll be able to like specify your group, and then It'll be one assignment for the whole group.
Okay.
Now, sometimes it doesn't work well, or students don't work well with Canvas or something, and it doesn't happen. But we only need one. Like, as long as the obviously the names of the group are on the write-up, then I can form the groups just fine. So, but yeah, there should be an option when you sign up to sign up as a group. So just do that. Sorry, I keep saying sign up. Like when you submit, to submit as a group. It'll be like a sign up to specify the group. At least that's what Canvas offers. Hopefully that's the user experience you have. I was saying some people are still asking about not having found having found a partner. So the rule still stands. You have to do this with a partner group of 2 or 3. There are presumably a few people in this position still. You should still submit something, but if you haven't figured this out yet, but I guess what I'll be doing is looking for, I guess, people who are 2 people or more that are in that boat and combining and just asking you to be in groups, and so it'll be assigned by me if you find yourself in that situation. Hopefully there's not too much of that, but from the emails I've gotten, there's at least a few, at least as of yesterday. Yeah, who knows today? And hopefully things like Canvas are helping to, like an online forum to be able to find a partner in that. Okay, any questions about any of that before? Yeah.
So in terms of the architecture, how well defined are you expecting that to be?
In the write-up?
Yeah, sure.
Like in the proposal? No, I mean, it doesn't have to be like all the details, right? Like that's the part, that part's to be kind of worked out in your project. It should just be something about like, I don't know.
Network.
Well, no, I mean, a little bit more than that. Like, I'm not saying, like, I guess what I'm saying is like, not hyperparameters of the network, but like this kind of a network. So it shows me that you recognize that there are certain networks that should work better for certain kinds of data. You know what I mean?
An example is in our topic, common things like pyramid-based convolutional neural network. Does that suffice to say something along those lines, or do you want to add it layout?
Yeah, and if for some reason it's not, I'll just tell you that, and then we'll figure it out from there. You might have to just reword it and resubmit it or something, but yeah, no big deal. Good. Anything else? Okay. We will continue then with generative neural networks, convolutional neural networks. Okay, so I said today we would do variational autoencoders, and I am a man of my word, so here we go. So remember what we did this last time is we came up with this model of how you might think of generating pixels by factoring the likelihood function of the data, meaning the likelihood being like the probability of being a member of the data set of interest or not, by factoring it into these conditionals. When I say factor, remember this capital pi here is a product. I never did say that explicitly, but maybe you've never seen that or you've forgotten what that is, but that's just, it's a bunch of products, right? It's like just a bunch of probabilities all being multiplied together. And then you're trying to maximize that. And the idea of the conditionals is that we've generated a bunch of pixels already. I want to generate the next one. I'm only allowed to condition on those pixels I've already generated. And then we kind of just step forward like that, adding pixels to the list of pixels that we've already generated. So as we do VAEs today, it's going to look it's going to look a lot different. We're actually going to be introducing a latent variable, Z. Now latent is just like one of these science words we use for hidden or unobserved. We've seen this a bunch already when we've talked about encoders. Oftentimes we think of like the encoding as being some kind of latent representation of the data sample itself. And when we have encoders and decoders, that's really manifest, right? It's like the idea is that we're trying to decode from this encoding or this code, this representation, this latent representation of the data point. And so it's something, the idea is that it's some smaller dimensional representation that captures the relevant information. We often call these factors of variation associated with the data point, and then we should be able to reconstruct the data point from those latent factors. So it's like a compression, and it's enough to allow us to reconstruct more or less faithfully the original data point. So what that would say is that there's like some redundant information in the original data point that I can compress down to a more compact representation. So Z is going to be the thing that captures that. So when we set up VAEs, we're actually just going to start from here. We're going to express. So again, the idea, remember, we're trying to model a probability distribution associated with our data set. In this case, explicitly. That's what this always is. This is just, think of it as a probability of a data point being in that data set. But what we're going to do here is we're going to, for some, unknown, probably like bewildering reason, we're going to express this probability as an integral over some introduced latent variable. And the way that we do that is we just use laws of probability and the definitions of our integrals and just say, well, this total probability is really the integral over all latent states of the likelihood of seeing that latent state, that latent variable Z or that value. We're going to integrate over some space. Think of like the full vector space, but this will be some probability saying like this is how likely it is to see this particular Z, and then you have this function here which looks like a generator, right? It's saying given my latent code, what's the likelihood that what's the likelihood of like generating the data point X here? And I'm just doing, the point of the integral is I'm going to compute these things over the entire latent space, and that will give me back the total probability of seeing that point X in my data set. So honestly, at this point you got to say, why are we doing this? This is bad. These are bad. Integrals are bad. We've loved being on computers, and computers don't like integrals, and why are we doing this? But it does give us a way of being able to formulate a way of learning this likelihood distribution that will be more powerful than methods like this for doing for solving this generative problem. So that's literally what all of today is going to be, is like, how are we going to deal with this integral, and how are we going to somehow get neural networks into here, and how are we going to get a loss function, and how are we going to train something. So buckle up, because that's what we're doing. All right, so there's a lot to this. So first of all, we just want to talk about autoencoders. We've already talked about this, but a variational autoencoder is one part variational, one part autoencoder. So we need to know what autoencoders are. And it's basically what I said, right? And we've seen these before. It's like an autoencoder is something that encodes a data point to some feature set. We often think of this, again, as I just said, the latent features associated with this data point. And yeah, I've said a couple of these things already. Whatever the encoder are, these days it's usually neural networks. Why are we doing this? Well, again, we're reducing the dimension. The point is that we feel like in doing so, we're going to learn the meaningful factors of variation for this data. How do we train something like this? We're going to have a second part to this, a decoder, whose job is the encoder's job is to take us to transform the input to these important features. The decoder's job is to take us from these important features and to reconstruct the original data point. This is a form of unsupervised learning because this is not requiring any labels. You can think of it in another way. The data itself is being used as a label. Yeah, as always, like if we're doing images, the things that we expect to see here are convolutional networks. Of course, these are now being done with visual transformers as well, but still a lot of convolutional networks being used here. Yeah, and the idea is that we have an input. We want to reconstruct this as faithfully as possible. Now, what's going to depend, what is the quality of the reconstructed image? What will it depend on? Well, it will depend on a couple of things. One is just like how powerful these networks are that we use for the encoders and decoders, right? If we use just like a couple of fully connected layers, or even just a couple of convolutional layers, we might not expect there to be a lot of capacity to learn this encoding decoding task. So like, you know, like the deeper and richer these networks can be, you know, the more likely we think we are to be able to reconstruct our image properly. The other thing is going to be also the dimension of the latent space. So like the number of dimensions in that vector z, right? Like if we make that be like one-dimensional, we're not going to be able to reconstruct high-dimensional data very well because we expect there are more factors of variation than just one, right? Like if it was just one, like this might be something like, I don't know, color, like you know, like some simple color, or it could be more complex, like a horse in front of a background, and then like the single feature, latent feature is something about like where that horse is in the image or something like that, right? I mean, it can be more complex like that, but there's only one degree of freedom that you're varying to get, you know, to produce the data set. So obviously, we expect it to need a lot more than that to reconstruct or to describe the important factors of variation in, you know, these complex data sets like ImageNet, CFAR10, and so forth. So it'll depend on those two things. So even if we have like the best encoders and decoders, we'll still need to make sure that we have the dimension of the latent space sufficiently large. And that you can think of as like a hyperparameter in a problem like this.
Is there anything that happens between the encoder and decoder in this architecture, or is that just like a checkpoint, like this is what things look like before they get passed to the decoder?
No, I mean this is literally the output of this encoder and then the input to the decoder.
And then but there's no usually architecture between those two. It's like doing
No, because if there was, it would be part of the encoder or the decoder. Yeah.
Just because these are not necessarily encoded decoders like transformers, right? Because in this case,
Right. It could be. It could be. I mean, like if we were doing, I mean, we did talk about these with transformers. Like if we were doing language, we could be learning an encoder decoder. We mostly talk about that in the context of neural machine translation. In which case, that's not auto-encoding because the output is different from the input. But you could train exactly those same things, but just have the output be the input, right, and reconstruct. But yeah, so this is a general kind of framework. You could do this for any kind of data. This could be images, it could be language, it could be time series, it could be all kinds of things. Of course, we'll be talking mostly in the context of images. Okay, so there's one more thing I was going to say about that. Oh, we often refer to this this latent layer 2 as a bottleneck. The idea is that we're trying to take this like high dimensional data, we're trying to you know, squish it through a narrow bottleneck, and you know, the idea being the thing that comes through there is just the essential aspects of this data. You'll hear that referred to often, just like this is the bottleneck. Okay, so how do these things get trained? We're trying to reconstruct the original input, so we want to penalize any variation or difference from that input, right? So whatever this output is, we want it to be the same as this input. So a natural way of doing that is to somehow calculate a distance between those two things, right? If these are like high resolution images, these are you can think of these as like very high dimensional vectors, but nevertheless you can still measure the differences, you know, in some space between them. And we often just, you know, do simple things with autoencoders like the L2 loss, right? So there's a simple like Euclidean distance between a very high dimensional vector or two very high dimensional vectors. And then this is a perfectly fine loss function. It's 0 when the two are equal, the predicted output and the input, and it's positive otherwise, right? And it's also a nice quadratic, it's differentiable, and you know, we can optimize this via the methods we've been learning. Again, doesn't use labels, it's unsupervised. This is all nice as well. Ideas like this, by the way, preceded, you know, a lot of what we see in like the way that neural networks kind of built, like the history that we saw since like 2012, right? Like we're very focused on like computer vision classifiers and those kinds of things. Ideas of like autoencoding really, you know, existed long before that, and in fact, there were a couple of years before 2012 where like some things kind of like autoencoders, it's not really the same, but there's some similarities, called like restricted Boltzmann machines, were being worked on and were being used and trained in like very similar ways here to like initialize the layers of very deep networks. In those days, like 6, 7, 8 layers, right? So anyways, the idea's been around a long time, and it's very natural in some sense. This is like the neural network nonlinear way of doing a dimension reduction, kind of like PCA is like a linear way of doing dimension reduction. Yeah, so like, what do you want to do with this kind of stuff? Well, if all you care about is encoding the image and compressing it down, after you're done with this training, you can throw away the decoder, or not. You can keep the decoder. The decoder is really cool, right? Because you take samples from your latent space, and then you can just, you know, put it into our decoder, and we get back, like if we train image data, we'll get back an image, and that's kind of fun to be able to visualize like the image associated with that. But you've got these two pieces. So that's autoencoder is pretty simple. What are variational autoencoders? So what's the variational part? Well, variational will have to do with like probabilities, and in particular like certain approaches to how we approximate probability distributions. And we'll see that as we go through here. But one of the really like cool things that comes out of this is that instead of having these kind of straightforward encoders and decoders, we're going to actually be sampling from distributions. So these encoders and decoders will actually end up being about like, they're going to give us the parameters to distributions, and then we're going to sample from those distributions. Now that's going to be kind of weird. We're going to put sampling from a distribution into our computational graph, and that is not a differentiable operation, just sampling. So we're going to have to deal with that in some way. But variational autoencoders were kind of like, you know, one of the original ways of doing something like this, and that became very popular. They used, and I'll show it to you, like something called the reparameterization trick, which is now used in a lot of other network training methods to introduce sampling into the forward pass. Okay, so let's start going through all this. So what would that look like? Well, like what would sampling, what do we mean by that? So we assume we have, you know, our training data, right? These XIs, and some way of generating the latent representation. So if we want to think about the decoder, we have these kind of 2 bits. If you want to think about these in a probabilistic way, we have these kind of 2 bits for decoding. We have our space, our latent space, and we talk about there being a prior on this space. Meaning it's just some sort of distribution that kind of expresses like where we expect what parts of the latent space do we expect to have like important information. So this could be uniform, right? This could be like equal information everywhere. This could be Gaussian, like more. We expect there to be kind of more concentrated information around the origin. This could be a lot of different things. But importantly, we can sample from it. We also want to be able to sample from this conditional, because this idea of sampling from this is the generation part, right? Once I have an appropriate latent variable, or have a latent variable, I can sample from this conditional distribution. So this will give me data points that are likely to be associated with this latent factor. So, I guess I just said that. What do we mean here? We mean, no, maybe I'll go back to this. Again, no, I already said this. These are, just keep in mind that what Z represents. It's something about like the information needed to generate a sample from our data set. Okay, so what do we mean by all this? Well, whenever you see theta in this class, W and theta are the giveaways that say that we've got parameters to a network. So these things are going to be, these probability distributions are going to be we're going to estimate them with neural networks whose weights we'll call theta. And we want to be able to estimate, the true parameters for our generative model, so the thing that's actually associated with our data set. How to represent this? Well, we are going to represent these pieces in 2 different ways. This right here, so let's see, what we're really trying to do is just generate an appropriate image. But we have these 2 distributions. And so we can decide kind of like where the complexity will go with respect to like going from, these numbers to something like very complex, like a high-dimensional image. And the way that we choose to do this is we go for simplicity here on the latent space. So we want our prior to be fairly simple. Simple means things like uniform. Very often in the variational autoencoder setup, this is a Gaussian. And there's reasons for that. We'll see a little bit more of that as we go along here. But we'll often just say, you know what, this is just a Gaussian, which means all we have to learn are simple parameters associated with that, right? It's mean, it's covariance matrix, and oftentimes we can even get more specific and say, this is going to be like this will be a Gaussian with a diagonal covariance matrix, meaning that the features are independent of each other. That's actually, if you start thinking about what we're doing, is we're now placing constraints on this latent space by deciding the criteria for the prior distribution, right? So if I say it's a Gaussian, great, that just means that I've got a mean and the sort of max entropy distribution around that mean. But if I start to say things about the covariance structure, then I'm saying something about like how the features ought to end up. So if I say we have a diagonal covariance matrix, we have 0 covariance, then we're saying we want the features to be independent of each other. That's not a bad situation. If you think about that, that makes a lot of sense. If these are really important factors of variation for generating my image, then they really should be independent of each other, right? It's like, this is like, I don't know, if we think about a single object and like its orientation in an image, we have things like location of the center of gravity of it in the image, and like how we're rotated in 3 dimensions around that. And each of those features doesn't depend on the other feature for what it is. And you could think about this getting more complex. If we're talking about like, I don't know, dogs and cats and people and cars and things like that, what the features we want to show up there are, we want things to be like, I mean, it never is this simple, although, well, it just depends on how simple the data set is, but we want things, we want these factors to somehow be associated with like clear concepts like color, and how that and all the other features, like to not depend on the color for their values. So anyways, coming back to this, however we choose the distribution here, this is going to be some kind of constraints on the latent space and the character of the features. So we often, in this setup, will just choose it to be a Gaussian with a diagonal covariance matrix. Okay, well that means, so that's a lot of simplicity. So then where is the complexity in being able to turn that into an image? Well, that's all going to be in our conditional function. And that is going to be our neural network. Okay, so that's something that we're going to estimate with a neural network. So simple Gaussian, complex neural network, together that's going to allow us to generate a complex image from a low-dimensional vector. How do we train a model like this? Well, remember this was at the beginning of the of the lecture. What we want to do is we want to maximize the likelihood of the actual data points in our data set of interest. Note that we've got these 2 pieces here, right? We've got our Gaussian and our neural network, and then to get to this, we need to do some kind of integral over the latent space. Like I was kind of alluding to earlier, there's a problem here, and the problem is this is an integral, and unless we've all had this experience, right? You learn about integrals and you're kind of excited about it, then you realize there's only a handful of integrals you can actually do, and the rest of them, it's like, sorry, it's a nice idea, but get a computer to kind of, to approximate it for you. And we could think about a computer approximating this for us. I mean, we will have an explicit representation of the prior, an explicit representation of this generative conditional. So maybe we could do this, but if this is if Z is, I always say low dimensional, but the sense of being fairly high dimensional relative to the problems we've seen in multidimensional calculus, right? This might be hundreds of dimensions, maybe even thousands of dimensions. Approximating this integral by doing approximating this with Riemann sums or something like that is also going to be extremely complex to do. Right? There's too many Riemann sums to get it right. So that's problematic as well. We really can't go along those lines. So what do we do? Well, guess what? There's a solution. Otherwise, we wouldn't have a lecture today. So simple Gaussian, complex neural network, intractable integral. So you might think, okay, well, what's the solution? Well, maybe we'll just deal with other distributions. But in reality, what happens is, so here's our posterior. Think of this as an encoder. Bayes' theorem gives us kind of this relationship between the prior, this data conditional, this posterior, and the full data likelihood, or what we often call the evidence. This doesn't help us, right? That thing is still there and it's intractable. So what do we do? So this is where the variational part comes in. So what we do is we say, okay, we need an encoder, we need a decoder, and we're going to somehow we're going to use those things to maximize the data likelihood. So the problem here is that this is complex, and therefore this is complex. So we just start to say, okay, well, let's start approximating things. So we say, okay, fine, we're not going to be able to do that integral, so let's not worry about that here. Let's just say, okay, let's introduce an entirely new function, q, and what we want it to do is approximate the posterior density. That at first you should say, well, how does that help us with anything? Like, if we don't know what this is, then why would introducing a new function to approximate it be helpful? Well, what it does do is it decouples some variables here that allow us to then derive a lower bound on this likelihood, and that's the thing that we end up optimizing. So this would be the first time when we've really kind of seen this, where what we're going to do is we're going to introduce a loss function that's really an approximation to the loss function that we want, but it's a lower bound on it. So hold on a second. I'm gonna over and over make the mistake of calling it a loss function. The loss function is it's what we really are. What the optimization problem here is maximizing what we're calling here the data likelihood or the data evidence, or the evidence. So we're actually going to be maximizing something. So this is going to be a lower bound, and we want to maximize this lower bound. So the thing that we want to maximize is bounded below by something that we can optimize, and by maximizing that, we're at least ensuring that the thing that we really want maximized is no lower than that lower bound. That does call into question, like the other piece of it. We'll talk about what that is here as we go through the next couple of slides. But the problem is, well, not the problem. Well, in this approach, there will always be some kind of uncertainty of whether or not we've actually, the optimization that we do is like enough to give us something good in the end. It turns out very often it does, but there aren't like too many guarantees there. So we're kind of taking a step into uncertainty here by doing this, but it does give us a way to deal with the intractabilities in these arising from that integral. Okay, so great. So we talked about sampling. So what does that mean? Well, we've got our two networks now. We've got our decoder network. This is going to be some network with parameters theta. That's going to take us from the input z to the latent variable z to like our data point x. But this is a distribution. We want the training of this to like respect that in some way. And the way that we do that is we say, okay, what the network's really going to do is going to output the statistics of a Gaussian distribution, the mean and the covariance matrix, and then we're going to sample from that. Okay. Similarly, for the encoder network, again, this is a distribution. It's going to be represented by a neural network with parameters phi, and it's going to go from it's our encoder, so it's going to go from our input to our latent space. It again is going to be giving us parameters for a Gaussian, and we're going to sample from those. Now these are different from the Gaussian of the prior on Z. So there's like going to be Gaussians all over the place here, but there's a difference here between these and the prior Z. The prior Z is a Gaussian, which we're going to end up fixing all the parameters on it, so we don't have to learn anything in it. But these decoder networks are going to be where the complexity lies, and we want to sample from them. So instead of this, being like taking the form of a Gaussian and just learning the parameters of it, we're actually going to learn to give us parameters for a Gaussian that depend or are conditioned on, in this case, the latent vector z, meaning like this could be different the mean and the covariance matrix could be different for different z's. And then we're going to sample from those. Same thing for the encoder network. So this is a way of explicitly representing distributions, but also allowing us to sample from them rather than just saying like, this is a transformation from one input to another, or like one sample to another sample in the distribution. GANs actually will work that way, and we'll see that next time, but this does not. Okay, questions so far? It should feel a bit confusing because it's like we're like in the middle of kind of this complex like setup for doing this. But these are like the elements of what's going on. So I just really wanted to make it clear that we're talking about learning neural networks that represent these distributions, our decoder distribution and our encoder distribution. And we really want these to be distributions in the sense that we want to be able to sample from them. This is be part of like the generative part of this network. And the way that we do that is instead of this just being a transformation from z to x, this is going to be a transformation from z to parameters of a distribution, and then we'll sample from that distribution, and that'll give us our x. So in the forward pass, in our computation graph, there's going to be a sample. And we're going to have to deal with that somehow because that is not a differentiable operation. Yeah.
Does Z have the same distributional parameters? I guess does the latent variable have the same distributional parameters in both the encoder and the decoder?
Yes, because we're going. Well, yes and no. Like, yes, in the sense that we want the overall, like we want the total distribution of Z to follow a very fixed, constrained, like distribution, like this, like very simple Gaussian. But these other ones, like take this for instance, right? So like what we're saying here, so this is going to be a distribution in the latent space Z, but it's going to be conditioned on our input. So it doesn't have to be, it doesn't have to match the total distribution because of the conditioning. Now, when we develop a little more of the kind of the theory here, we're going to see that there'll be a term in our loss function that will like deal with this exact thing, and we'll talk a little bit more about it when we see it. But note that just the fact that it's conditioned on here, it does allow us to for there to be, say, lots of little distributions that, as we kind of like range over the full input space, give us a simple distribution, over Z. Like if you again think about this as like integrating out the x, then we would get this like simple Gaussian over the latent space Z. Good question. Okay. Right, sampling. We'll be sampling from these conditionals. Given a Z, sample an x. Given x, sample a Z. Okay. So, what are we going to do here? Well, we need something to optimize. So like we said before, we want to optimize the data likelihood or the evidence. So probability or likelihood of the data point. Remember, like when we're training this thing, every single data point will be a data point of interest, right? Like that's what our training set gives us. And so when we're doing this training, we're basically for every data point, like all the images in our data set, we want to maximize this probability, right? Because these are the examples of what's in our data set. So oftentimes for numerical reasons, also for like information theoretic reasons, we'll take the log of that, the log likelihood. It has better properties for optimization in particular. And we will, so this is the thing that we want to optimize. This is the thing that for all of our data points we want to make as large as possible. Now notice I didn't put I didn't put a negative sign on there. In the past we've done this. That negative log likelihood, that's a proper loss function. Minimizing that means, you know, we're like in this case, we're getting to our goal of assigning a probability of 1 to the data point of interest. But we're not going to do that here, and you know that it'll become more or less obvious why when we kind of work through all of this. But anyways, just wanted to point that out. Okay, so now we're gonna like derive all this kind of crazy stuff. All right. So what's all this crazy stuff? Well, the very first thing that we're going to do is we're going to introduce this expectation on our latent variable z. Now this should look really strange because there's actually no z here at all. So like, why are we doing this? Well, remember what we want to do is we do want to work in the z somewhere here. So this first equality, by the way, there's a lot of white here. It's going to be filled in with all kinds of great math. So notice that how high this is. Like there's going to be a lot of math. But the very first thing that we're going to do here in deriving this like bound that we're going to optimize is this step right here. And why is this an equality? Well, this is a constant with respect to z right now. We haven't factored p into its into its prior and to the conditional. So when we do this integral, this expectation is just an integral with respect to this probability distribution. So this is a constant we factored out. This is an integral over probability distribution. It integrates to 1. So we just have this times 1, which is this. So we're doing one of those cute things in math that like it took somebody who knows how many months to figure out, and in one lecture period I try to make it obvious to you that why they did that. Right? So that's the burden on me. So there you go. That's what's happening here. But the whole point is to introduce dependence on z. Now, note something really interesting. What we've done here is we're saying the expectation, over the variable z with respect to this distribution. Remember, this is our decoder, but it's the thing that we introduced to estimate the true decoder distribution, right? So this is q phi not of z given x, not p theta of z given x. And this is where this is what we call a variational approximation. This having done this will separate. It'll separate the q phi from all the p thetas that are going to show up when we do more math here. So that's really useful too, so that we're going to end up having things that we can solve, things that are tractable. So anyways, all right, so hopefully the first equality here makes sense. The next one, the next one is just to use Bayes' theorem and just write this probability conditioned on z, right? So we have our decoder, like our decoder, our prior, the two things we talked about before, and now we have this sort of like true encoder that this thing is going to try to approximate. All right, so notice that we did, just for simplicity, we've dropped the fact that this expectation is over this distribution, but just remember that E z is that expectation. Okay, so we haven't done anything. We've just sort of rewritten things given identities that exist from things like Bayes' rule. Okay, then we do more of these like tricky math things that you should say like, oh, that's not so obvious, but whatever. It's going to be. You just have faith that it's going to be useful. So we work into here this approximate encoder, q phi. And we do that just by, multiplying by 1 essentially. This tricky multiplying by 1. It preserves the equality, but now we have these. We have this other distribution in here now to work with. Okay. What do we do next? Well, we do two things. We notice that we've got logarithms here, and we're going to split this whole kind of crazy mess up here into 3 terms. These are think of these as all like as factors, like a product, and our log factors over those products nicely, and our expectation is linear, right? So we get this kind of nice, we get this nice factorization and distribution of the operator over all this. So why these terms? Let's look what we've got. We've got a term here, EZ, where the Z is sampled from our approximate encoder of the true decoder right here, P theta of X given Z. So that's kind of interesting. We're sampling from the approximate encoder and then decoding that. Notice that the XI here and the XI here are the same. Right, so we've sampled the Z from our approximate decoder given our current data sample. Basically what we're wanting for the decoder to reconstruct that with high probability. So like this term right here, if we're maximizing this, we want to maximize this. And so this is a kind of reconstruction error that we want to optimize. It's not really an error. We have a minus sign on there would be an error, but this is by maximizing this term, we are maximizing the reconstruction to give us back the data point we started with when we did encoding and then decoding. So making this as close to 1 as possible, making this this whole thing 0, and all the rest of the terms are negative. So that is maximizing. This is a kind of reconstruction. It looks different, obviously, from the reconstruction we saw before, where we have like x and x hat, the some sort of distance between them, but this is like a probabilistic term that controls the reconstruction. But again, we've done this nice separation where we've separated the approximate encoder from the true decoder. Okay, so that's that term. Then we factored it. So like that was this term right here. Then we bring these 2 terms together, the Q phi of Z given X, and then this P theta. This P theta shows up down here. That's why there's a minus sign. So that's interesting. This is something about the approximate decoder and our true prior on the latent space. And then we have, so this is like, think of this as like some kind of comparison between the 2 of those. And then we have this term right here, which is the approximate encoder and the true encoder. And again, some kind of comparison between the 2 of them. Okay, so just got to get some sort of sense for those. Remember that the Z's here are being sampled with respect to the distributions that show up here in the numerators. And therefore, if you can recall, or I'll just tell you again, these expectations look like things we've talked about in the past. This, because again, this expectation is with respect to this distribution in the numerator, this term is the KL divergence between these 2 distributions. If you remember the KL divergence, this was almost like a metric between distributions. It's not quite, because it doesn't satisfy the triangle inequality. But, no, sorry, these are not symmetric, which actually I guess leads to that. But the point is that this is 0 if and only if these 2 distributions are the same, and it's positive. Forget the negative sign there, and it's positive otherwise. So these are really nice because it's 0 says they're the same, positive says they're different. Same thing here again, because we have a Q phi in the numerator and the sampling here is with the expectations with respect to that distribution. We also have another KL divergence between the two distributions that show up here. Okay, so what does this all mean? Well, I've already talked about the fact that this is a reconstruction. See? Yeah, anyways, these are nice KL terms. All right, so I've already talked about the fact that this is giving us a really nice way of thinking about reconstruction here. What are these other terms about? This is, let's see, maybe, okay. Actually, before I get into the explanation of this, let me point out the thing that's being pointed out on this slide so I can follow the presentation of the slides. Remember that, like, somewhere hidden in here was an intractable integral. And what was it? Well, it's this thing right here, p theta of z, this true encoder. This gave rise to the intractable integral. It was the whole reason why we introduced an approximate encoder, q phi. So there's an integral going on here, and there's a problem. Well, this just includes a term that is intractable, that we can't compute from the pieces that we have included in this derivation. So things are still problematic in the sense that, like, we couldn't just go and optimize this term right now. But there's something really nice about the property, but the fact that we've been able to express this as a KL divergence. Two things. One is we want we do want these two things to be the same, right? So we do want the KL divergence between these two things to be 0. So even though we can't really compute it, we want it to be 0. And it's a KL divergence, so it's either 0 or it's positive. So, if we look at these other terms, this is something that's nice, right? We're going to have an explicit form for this Gaussian. We're going to have, this is going to be a neural network, but we can remember this is going to be another Gaussian whose mean depends on the input x. Whose mean and covariance structure depend on the input x. And then sort of similarly here for the decoder, just the other way around. So these things are tractable. These are things that we can actually deal with because of the form that we've given them. This thing is not. But this thing is 0 or positive. So it's non-negative. So we can actually now say, okay, because this is non-negative, the rest of this term here, the rest of this part of the equation, is going to be a lower bound for the thing that we care about maximizing, the log of the data evidence, or likelihood. And so this is where that approximation comes in. We got to this point, and we're actually going to say, you know what? Forget this. We're not going to deal with this. We're just going to recall that, this property of being non-negative, and we're just going to focus on optimizing this right here. This is a lower bound. It's often referred to as the elbow, the evidence lower bound it's a lower bound on the evidence. You'll often hear it or read about it as the elbow. And this is what we're going to optimize. Now, we'll talk a little bit more about this term right here in just a second. But we'll be dropping this. But what we really will be doing is really hoping, perhaps beyond hope, that this term is as small as possible. Because the smaller it is, the closer our approximate encoder is to our true encoder. But then we're just going to kind of say goodbye and say, hopefully we did a good job here. Okay, so I'm gonna stop here for just a second. I try to slowly walk through this, the math here, but there might be questions, and there might even be like meta questions like, what on earth is going on here? Like, why are we doing this? Hopefully we'll answer some of those questions in future, in the next couple of slides. But, yeah, just stopping for questions.
It looks like the entire thing, we are doing all this work with respect to a single data point. Why are we doing that instead of before the previous slide when we looked like we were wanting the entire data set?
Well, in the previous slides it was just an X, right? So we just kind of made it clear here that this is a particular data point in our training set, just by calling it XI.
Okay, that doesn't change anything about it.
No, because like really what's happened here, notice how we cleverly wrote this by saying, L indicating loss. This is like, this is the contribution to the loss for this single data point. In the same way that we've always done this for, when we've optimized our loss functions, they're typically some kind of, aggregation, use like an average over, the total loss for the batch is the average loss over all the samples in that mini batch. So that's going to be the same thing here. This is the contribution of that particular data point, and when we do mini batch optimization here, we'll be averaging those for the entire batch. Good question. Other questions? Yeah.
Is that probability of x given z and exact posterior, or is that just what we're approximating versus exact?
Right. Sorry. This one right here, x given z.
Yeah.
Yeah. So like, this is exact in the sense that it's going to correspond to the chosen prior. That's why we persist this theta here and here. So it'll be exact, although we're going to be estimating it with a neural network. So there's like kind of two things. There's like two estimations happening here. One is, there actually is a true exact posterior, and we're going to try to estimate it with the neural network. And then there's this other one that is there's actually this neural network estimate to our true posterior, and then we're going to estimate that with an entirely different set of parameters. So that's why we go from p theta to q phi.
Okay.
So it's kind of two levels of estimation there. It's a little bit hard to talk about because of that, but so there's actually the true posterior for the data are approximations with neural networks, and then a second approximation with a different neural network, the error that we're making there is going to be determined by this intractable KL divergence term. Does that even?
Exact-ish.
Yeah, lots of approximations happening.
Yeah.
Should this even work? The only way you know is you just go and try it. Some crazy people did, and it seems to work actually really, really well. In fact, there's tons and tons of variational autoencoder formulations of all kinds of interesting things. This is just sort of like the kind of, if there is a plain vanilla version of this, this is what it is. Okay, great question. Okay. Yep. Variational lower bound. Elbow for evidence lower bound, and this is the optimization I was talking about. Your question, Chris, is we'll take a mini batch of size n. Here actually this is the sum, not the average. Doesn't really matter. It's all the same. But we kind of abuse this. We keep talking about this as a loss, but really in this formulation we're trying to maximize these terms, not minimize them. Okay, so what does maximizing do? Yeah. So what does maximizing do? Let's look more carefully at these terms. We talked about this already a bit. This term right here is about reconstruction. So we have two networks that we're learning, one with parameters theta, one with parameters phi. we first are going to sample from our encoder. So we're given our the point xi in our training set. We're whatever the parameters are right now for that network, we're going to sample a z. So that's the encoder part, and then we're going to decode it with p right here, and so what we're saying is we are sampling, but what we're saying here is not necessarily giving a sample. We're saying what is the likelihood that the point I decoded to z is actually going to be reconstructed by the network p theta, given that z. And if the likelihood is really high, if it's close to 1, this term right here is going to be very close to 0. Otherwise, it's going to be negative. And it could be, if this likelihood is really small, the log likelihood is going to be very small, very negative. So by maximizing this, what we're saying is we're making the encoder to z and the decoding back to xi. Oh, sorry, I should say it this way. The encoding of xi to z and the decoding of z back to xi, we're making that consistent in a probabilistic way. We're assigning likelihoods. We're saying we want to make the original data point as likely as possible when under the probabilistic decoder. So that's what that term is about. It connects the approximate encoder with the true decoder. Sorry, the approximate encoder with the true decoder. So this is like playing the role of x, like the square of x minus x hat. Now, what about this term right here? So if we're maximizing this, remember the KL divergence is non-negative. So the negative of the KL divergence is non-positive. So it's making a negative contribution. We're trying to maximize. So the way we maximize is make that as close to 0 as possible, right? So what would that mean to make this as close to 0 as possible? That would mean, remember, we're going to fix this. We're going to fix this posterior right here. Like literally, the way that we typically do this, you have a lot of choices here. And this is what's kind of fun, maybe about this technique. But we're just going to call it. It's going to be the simplest Gaussian. It's going to be a standard normal. In high dimensions, it's going to have a mean of 0, and it's going to have a covariance matrix. That's the identity function. So it's diagonal, and so all the covariances are zeros, and each of the variances is 1. So this is, in high dimensions, this is a standard normal distribution. So what this term is trying to do is it's trying to make this conditional distribution, this encoder, it's trying to force it to have these properties right here, which is kind of weird if you think about it. Because actually we do want the z's to vary given x, right? We don't necessarily we don't necessarily want this to be devoid of the information of x, given here in x. But what we do want is that as a distribution over our data points, we want it to be as close to this as possible. So this term right here is really interesting. It will very often, especially for very complex data sets like our image sets, it'll very often this distribution will not just be the standard normal distribution. We'll actually incur loss in this KL divergence because we do need information about x when decoding z. But it's a trade-off because what that should allow us to do is to perform this reconstruction much more faithfully. So there's like these two things. It's not really adversarial because it's like in the sense of how we've talked about it before, but there is a kind of trade-off between them. If I can incur some loss here and have my encoder be dependent on my input, I only want to do that if I get if the gain here in being able to reconstruct is greater than that incurred loss. And they kind of play off each other, and that's why there's that negative sign in there. So that's to give you some kind of understanding of what these two terms are. Now, of course, we would love to have this in here. This would be, you know, this would make sure that we actually had the posterior, or the true posterior distribution, the true encoder. But it's intractable, so we don't. But you know, the better we are, like the more we maximize this thing, the more likely this thing is going to be 0 anyways, and so we just kind of hope it is. Okay, so we put it all together. So this is our loss function that we're actually, when we optimize it, we're actually maximizing it, not minimizing it. What happens? This is following all the paths. So we're given an input that goes into Q of phi. That'll give us a mean and a covariance, a mean vector and a covariance matrix that depend on X. And then we're going to sample from those. We're going to sample from the normal distribution with this mean vector and this covariance matrix. We're going to sample the Z. So this is how we get to, this is how we do the encoding. And then we do the decoding in a very similar way. Our network takes us to parameters for another Gaussian, mu of x given z and sigma of x given z. We will sample from those and get our estimate for the reconstruction of x. And that's, you know, going through this whole thing is, when we maximize this, we're making sure that there's consistency as we go from x to z back to x hat. And again, the KL divergence term there is trying to force this to be just a very simple Gaussian, but we'll give up, you know, some loss there if doing so allows us to do this reconstruction much more faithfully. Okay, questions on that? Yeah.
The decoder in this step is trying to reconstruct the prior, is that right? Given the data that it's given, or just
the encoder is trying. So this term right here.
Sorry, yeah.
The encoder is, this term is trying to match the encoder to the simple prior. Right. So it's saying, like, you know, so like, remember what I said earlier. So so what does it mean to be like this? It means that, like, if you know, again, we've chosen the standard normal. So it means that all the features are independent of each other. That's why we have 0 covariances. So that's kind of nice. It means that all of the features are on the same scale, right? They all have mean 0 and a standard deviation of 1. So that's nice too. Like you know, like they're, like one's not like overweighted or underweighted. So like those properties are nice, and so we're trying to get at that. But like it's also going to try to deviate from that given the input, so that we don't just like end up always like close to 0, right? Because that's like for complex data sets, that's almost certainly beneficial in terms of doing the reconstruction well. So they're just going to kind of play against each other. Right. So this is the forward pass through this network, and now we want to back propagate. So the back propagation is a problem because we have these sampling steps. So, well, what do we do about that? Well, it's really nice that we chose Gaussians. And why is that nice? Because there's a really simple way of taking a sample from your standard normal and turning it into a sample from any other distribution. And the way that you do that is you just take your sample from here, you know, from your standard normal that doesn't have any parameters in it, and you multiply it by the square inverse of the covariance matrix, and then you add to it the mean. So this is just like, this is one of those, or sorry, not the inverse in this case, going forward. You want to just, you want to multiply it by the square of the covariance matrix, the square root of the covariance matrix. I've said a bunch of things wrong there. You want to multiply it by the square root of the covariance matrix on both sides, and then add to that the mean. So what that does, that's called the reparameterization trick, and what that does is, wow, that just kind of got weird. What that does is the sampling then, you can just sort of sample outside of the forward pass. You can just like if you have a mini batch of 10 and you need, so that therefore you need 10 samples from Z, you can just do that outside of the forward pass, and then you can just use those as like constants in the back propagation. And so we will back propagate through these, but the sampling won't be there. These will just appear as like constants that sort of like magically appeared outside of the forward pass. So, or outside of the computation graph. So this is like really, really nice. It's really simple, and it's even though it's like deceptively simple. Well, even though it's simple, it's like deceptively simple. It's like a very powerful technique for allowing sampling from distributions to happen within a computation graph. So again, like the whole idea here is simply that we do that. Now, here we are thinking about what this latent space looks like. So how do we generate images from this? Okay, so once the whole thing is trained, we now want to sample from our distribution here. I mean, we don't have to sample. We can do anything we want. We can just like pick fixed vectors in here, or we can sample from the prior or whatever. But we can take a vector in our vector space, in our latent space, and we can decode it, and that'll be an image if we trained with image data. So here's an example of training on MNIST. Remember MNIST? Fun MNIST? It was it was all these handwritten digits from 0 to 9, right? So here's an example of having trained a variational autoencoder on MNIST with only, well, this could be more than that, but so with who knows how long or how many dimensions the latent space has, but if we focus on a couple of those features in there and vary them, what we see are the images that come out of that. And what's really cool is that you can see right away that these parameters are parameterizing the data set in like very like comprehensible ways, right? So if we look at this, just pick any row. Let's just pick like this bottom row here, maybe it's easiest to see. So Z1 is some negative value here, say. What happens as we vary Z2? Well, first of all, looks like we've got something like, starting with something like a 7. But as we move along this axis, the Z2 axis, we kind of turn into a 1 at some point. And then that 1 seems to like kind of rotate from being like a line drawn from top left to bottom right to the opposite, like top right to bottom left or bottom left to top right. So kind of it's changing the angle that 1 is positioned at with respect to like the bottom of the image. And if you look through all these rows here, you kind of see that persist. It's sort of easiest to see there, maybe at the top row as well. This top row started with 6s, and then after varying Z2 a little ways, it got to be 0s, and then these 0s started to be more and more tilted to the right. And you can see this with a lot of these 8s. But the point is that each one of these parameters, Z1 and Z2, when they come together, there's some point in our latent space, whether it's 2-dimensional or whether it's higher dimensional than that, we're only focused on the first 2 features. What we're seeing is that these sort of trace out samples from MNIST. None of these are actually in MNIST, but they look like samples from MNIST, right? They have that kind of handwritten feature, or handwritten look to them. And basically these factors of variation are controlling like what number is appearing, and something about the style in which it was written. And it's really cool when you look through this. Like you're seeing very smooth transition through the numbers, right? So like you notice how like 7s got turned into 1s. Like the smooth transition is that like the top line of the 7 is sort of getting smaller and smaller and smaller, especially as the base of the 7 sort of tilts up to vertical. And you have the smooth transition from 7 to 1s and these different kinds of 1s. Take any of the other rows, you sort of have the same thing. It's like, we're here, like we have a bunch of styles of 9s, and then those 9s sort of like transition to 3s through these like 8-looking things, and that's not surprising because there's a lot of 8s nearby. And these get turned into 3s, and then these 3s kind of start to tilt backwards, and you can see these 3s are starting to turn into something else. It's not exactly clear what they are. But again, what this is trying to show you is that these factors of variation that we learn in the latent space through this procedure correspond to things that control the image, things that control what actual image gets decoded. It's kind of hard to say what they are. There are other data sets where you can literally an interesting, very simple data set, this simple faces data set. And it's literally just got it's like a bunch of graduate students got together and took pictures of themselves, of their heads in like a variety of it's just like these portraits, but like, carefully turning to the left, carefully turning to the right. And you can see like, for instance, it has different kind of properties like going from frowning to smiling. And this was trained, this thing was trained on this data set. And notice that, just like we saw with the MNIST, we have these latent factors, but they seem to correspond to something maybe that's a little bit easier to understand. This just happened to be that because these are like the important factors of variation in this data set, that Z1 sort of corresponds with higher Z1 being frowns and lower Z1s being smiles, and the V2s seem to be something about the rotation of the head, right? So this is looking to the left as you vary Z2, looking forward, and then looking to the right. And again, this was trained in an unsupervised way. This was not trained with labels saying, hey, you've got smiles and you've got rotations. But it's a natural way for this very simple data set to have been to assign factors of variation to how one would generate a face in this data set. And that's actually like super cool. And one of the great things that comes out of this variational autoencoder approach is just the way that you can think about and interpret the latent factors as generating our data in some way. We've run out of time, so here's when we start using the I metric. So here's a variational autoencoder trained on CFAR10. Unfortunately, if you look at these things up close, you're going to probably have the same feeling that we had when we looked at the pixel CNN results, right? Like, again, like you stand back, they look like they might be from CFAR10, but up close, like, there actually is maybe more structure to the semantic structure to the objects in here, but again, kind of really lacking. And you can, we're getting better at generating faces as well, but you can see that these are really, really blurry. Like that's the thing that kind of just shows up in these, and it's actually a problem with the variational autoencoders because they are formulated using this maximum likelihood, estimation method. Like that's how we optimize these things. And what's happening is like this. Well, we're running out of time. But I'll just say this briefly. What's happening when as we look at these data sets, like it's starting to look a lot better. There's colors and things like that. But why is it fuzzy? Well, it's fuzzy because remember that images are really interesting in the sense that you know, like there's a certain pixel arrangement of pixels that's a nice clear, you know, picture of a face, and then, you know, you don't have to change too many pixels and change the values of those too much before all of a sudden this is like a pretty bad picture. Like you don't, like it's fuzzy or something like that. So like, if you think about it as distributions, you have this high dimensional, like, you know, pixel space. You know, sharp images of faces are like these really narrow modes of a distribution, and then everywhere else there should be zero probability. And that's kind of hard to learn in these maximum likelihood estimation methods, because they tend to average over nearby modes, these like spikes in the distribution. So the next time we get together, we're going to talk about GANs, which is a way of overcoming that, and it's the method for generating very sharp images. There's some more here on like denosing autoencoders. You can look at that. It's nothing worth going through right now. This is what the pros and cons I just talked about. Next time we'll talk about GANs and how they solve the the blurry image generation problem. All right. Thanks for sticking around for a few more minutes. Good luck getting your proposal.